Welcome back after the break, everyone. We're going to launch into our study of magnetostatics. And as the name suggests, magnetostatics is the study of static magnetic fields. So that is going to be the focus of our attention for the next few lectures. Many reasons to study this field. One of them, for example, let's think medical applications. If you went and had an MRI, you would be put into a large magnetic field. If you were looking for iron ore, perhaps, and other minerals, you might measure the Earth's magnetic field. Similarly, if you wanted to navigate, you wanted to use a compass, you might measure the Earth's field. So many reasons for this. There's a whole list of them. This is just 3 examples. Now, our development of magnetostatics is going to parallel our development of electrostatics. We're going to take the same kind of approach, and I'd like to remind you of how we developed electrostatics. We developed electrostatics by considering a very simple experiment. Okay, so what I've drawn here are 2 charges. This is charge Q2. It's located at position vector R2 relative to this coordinate system that I've drawn here. Here we've got charge Q1. It is located at position R1, and I've drawn the vector connecting the 2 charges, which is vector R2 minus R1. You'll notice the signs are correct. If I add R2 minus R1 to R1, I do indeed get R2. Now this expression here is the force, but very specifically the force on charge 1 is the force on charge 1 due to the presence of charge 2. You'll notice that there is a constant out the front. This is due to our choice of SI units, that the force is proportional to the product of the 2 charges, and that it operates in the direction of this unit vector. This is the unit vector R1 minus R2 hat. This is not the vector unit vector R1 minus unit vector R2, right? This is take R2, subtract it from R1, and then normalize to create a unit vector. I'm going to bracket that off so it's clear that that is indeed a unit vector. The term downstairs is the square of the distance between the 2 charges. And so this force law, the Coulomb force law, tells us, it describes mathematically our observation that the force operating on one of the charges due to the presence of the other one decreases as the square of the distance between them, that the force operates along the line connecting the charges, and furthermore that the sign can be attractive if the charges are of opposite sign, or repulsive if they are of the same sign. Now you'll remember in electrostatics that our next step was to rewrite part of this equation as an electric field. We really invented the electric field at this point, and we're going to write down the electric field due to the presence of charge Q2 at the position of charge R1. Okay, so let's study those 2 equations. This is the electric field at position R1. So we're asking, what is the electric field at this point here due to the presence of charge Q2 at position R2? Alright, so I've denoted it E2 at R1, the electric field due to charge 2, but we're evaluating it at position R1. We've included the constants here, which are due to our choice of SI units. The electric field is proportional to the charge and depends on the sign of the charge. The electric field is in the direction of this unit vector. Let's check that we've got it round the right way. If Q2 is positive, the electric field should be away from the charge. Well, it is indeed away from the charge. R1 minus R2 hat is in the opposite direction to R2 minus R1. It's a negative of this, so it is operating away from the charge, or the electric field is pointing away from the charge. and furthermore the electric field decreases as the square of the distance between the charges. We can then rewrite our force law, this force law here, by multiplying the electric field by charge Q1. And this was the procedure that we adopted in our early development of electrostatics. We then made what might seem to be a rather trivial change in notation, and it is trivial, but it is also very powerful. And we moved to a notation where we denoted the position of source terms in the electric field with a primed coordinate, and the observation point where we would like to know the electric field by an unprimed coordinate. So let's do that. Alright, so let's have a look at this formula. Here we've got a position Q, a charge Q at position R prime, and we'd like to know the field E at position R. So we'd like to know the field, the electric field at this point. Well, the electric field then is given by this equation. Again, our constants. Electric field is proportional to the charge. It decreases as the square of the distance between our source term and our point of observation, and it is directed away from Q if Q is positive, and it is directed in the direction from Q to our point of observation, so from here to here. Okay, so the next step that we took was to rewrite our charge as a charge density. So in other words, an object, say we had some distribution of charge, and that distribution of charge, and this was described by a charge density, which I'm going to call rho of r prime. So now, if you like, we could write a differential element of charge as dq be rho at r prime. I'm going to write the volume element as d3r prime. Now, all I mean by this is it's just a volume element. In Cartesians, it would be dx prime, dy prime, dz prime, and in other coordinate systems, we would write it out appropriately. So that is my notation for the volume element, d3r prime. If we were then to substitute this equation, this expression for dq, into our electric field here, and integrate over the charge distribution, we would obtain the following expression. And this becomes really our most general expression for an electric field. The integral, of course, is over the volume that defines the charge distribution, so it would be over this volume here. With this equation, we were then able to study properties such as the divergence of the electric field and the curl of the electric field. And this, we began to learn about this BC electric field and some of its properties. In taking the divergence of the electric field, you'll remember that the divergence operator operates only on the unprimed coordinates, and so we can bring it inside the integral. Okay, so there is our expression for the divergence of the electric field, and you may remember that this term here, the divergence of that unit vector, is in fact 4 pi times the delta function. That delta function then removes this integral that we have here, sets r prime equal to r. Furthermore, this 4 pi cancels that 4 pi, and we wind up with the first of our Maxwell equations. This, of course, became the basis of Gauss's law. If we were to take the integral of both sides of this equation and use Stokes' theorem, we would find that the integral of E dot dA is the enclosed charge divided by epsilon naught. Furthermore, we could run a very similar kind of calculation and we could calculate the curl of the electric field, and we did do this, and we would find that the curl of the electric field for electrostatics is equal to 0. Right, so this was our program in electrostatics. I'd just like to remind you of what we did. When we developed electrostatics, we considered a simple experiment, two charges. We asked the question, what is the force on one charge due to the presence of the other? We developed the idea of an electric field. We studied the electric field by taking its divergence and by taking its curl. In the next segment, we're going to follow a very, very similar development of magnetostatics. We'll study a simple experiment, we'll write down a field, and we'll calculate the divergence and the curl of that field.